Thank you, Shubha. Yeah, thanks very much for having me here on this Friday morning. Yeah, again, I really would prefer that this talk be interactive. So actually just raise your hand and I think the moderator, Shubha or Yop, would interrupt me. And yeah, so I'll be presenting what we've done in Orange Quantum Systems and the Aqua Group in Leiden about the interfacing of Quantify and Quantum Inspire using a relatively simple variational quantum algorithm. And we'll be presenting the experiences that we've encountered there. So why did we actually want to do this? We wanted to actually figure out what are the important features, well, interface-wise, for a quantum computer to run near-term algorithms. Therefore, we restrict ourselves to only public APIs. And that also conveniently meant that we would do it on the Quantum Inspire platform that is already widely accessible. And this is actually a reflection of the current state of actually running a variational algorithm on a cloud-based quantum computer. And in doing so, we hope that our study here can help provide a bit of clarity on what infrastructural changes are needed for the next Quantum Inspire. If I may, the Quantum Inspire, which can be useful in the near term and especially useful for algorithm designers such as some of you in this audience here. So how did we do it? We first settled on the simplest, of course, NISQ algorithm, and that is the variational quantum algorithm eigensolver on hydrogen. It just needed 2 qubits, so it's the simplest. And since we in Orange Quantum Systems, we are also building Quantify, a package which I will be introducing later. We also figured, let's have an algorithm expert within Aqua in Leiden, and have her or him, and in this case it's Xavi from Leiden, to write the algorithm for Quantum Inspire, and we figure out how to interface that with the Quantum Inspire platform. Since he was already well versed in CIRQ, then we had the translation layer to convert the CIRQ circuit objects to CIRQ, and Quantify handles the rest of the experimental controls and the data management, as well as the timings and the profiling. So an introduction to Quantify, what is that? So Quantify is primarily used in actual experimental setups. It is an open source framework for controlling experimental quantum computing. It's heavily inspired by PIPE. It helps the user program a quantum experiment on hardware. But in this case, well, we're moving the concept up a few layers in the quantum computing stack. So for us, only the Quantify core and the CIRQ and Quest circuit simulators were used for the study. Quest was primarily used to test out the CIRQ to CIRQ translation module, in the sense that now we can be sure that the same circuit can actually be run on the Quantum Inspire platform, at least locally in our development machines. And yeah, as we've seen just now with all the dependency graphs, Quantify is made up of quite a few more modules, and Orange QS provides a few more proprietary advanced calibration modules, in particular the AutoDep graph and these lab-specific experimental libraries. And these are used to run the experimental hardware a bit more efficiently and more automated. If we've got the time later, I'll also be showing Quantify Scheduler, quite an interesting module, which is also open source within Quantify, and it provides pulse level control to algorithm designers amongst yourselves here. The most important core concept within Quantify Core, we've got the module within Quantify, for which we used were the measurement control and the settables and gettables concept. These are simplified experimental concepts which enable us to virtually control any type of experiments, or in this case, if it's in the upper layer, then it will be the simulations. Measurement control relates to the control flow of the experiment. It addresses the how, where, and when parameters need to be varied, measured, and stored. Settables and gettables relates to the variables of a particular experiment. So it addresses the what are the parameters that have to be varied, measured, and stored. And in our case, the angle parameters would be the settables, and the corresponding cost function or the energy levels, and as well as the expectation values, and also even the timing profiles are our gettables. And within the Quantify framework, we almost get the data storage and analysis management for free, which I will show later on in the demonstration. Then within the actual work itself, to translate it down to the Quantum Inspire platform, within Quantify Core, we created this circuit translator, and that actually translates the circuit objects to C COSM. And that is a COSM dialect which is supported by Quantum Inspire, and that enabled us to use the Quantum Inspire SDK and send the jobs over to the STIM2 and the StarMon 5 backends. As for a little bit on the algorithm side, this was primarily done by Xavi, is one of our partners in the study. The circuit ansatz was created in CIRQ, and it comes from the Braff-Yekitaev transformation of the Hamiltonian to the Pauli operators. If you notice, we actually use 4 parameters here, and that was the initial part of the study was, okay, we hope that some noise could be mitigated, but I think theoretically only 1 is required to reach the exact ground state of the hydrogen molecule. I think it's the beta angle. Yeah, so the circuit would start with the initial Hartree-Fock state, and then when we eventually run the VQE algorithm, then the classical optimizer will try to find the parameters which would then correspond to the ground state of the molecule. More details of it, I think, would be presented in the archive paper soon to be published, maybe in a week or 2. Yeah. So we actually ran the VQE algorithm across the bond lengths for a noiseless CIRQ simulator. And so these are the individual bond lengths that we run this VQE algorithm. And once we have obtained the optimum angles for each of these bond lengths, then we use these angles and send it over to the hardware backend runs. So yeah, you can consider that as some sort of a fake VQE. So instead of thousands of function evaluations, which the cloud API for Quantum Inspire is not designed for, we needed only 23, so 1 per bond length. Yeah, that is, you can actually argue that it's not a variational algorithm, but I counter that by saying that it's an optimization loop with 1 iteration. That's it. The results show that there are lots to be improved. As you can see, yeah, the errors are relatively quite huge compared to the exact energy. And it could be maybe improved via noise mitigation or improvements with the gate fidelity. We could not see any noise mitigation since we did not run any, of course, classical optimization loop within the hardware. So that actually meant that, yeah, there's some lingering nagging thing which we didn't really like. So not intent to just give that conclusion a rest, we actually decided to investigate the energy landscape from the hardware and the circuit simulators. Therefore, we changed the circuit to fix the alpha parameter to pi. And I think that initializes the circuit in the 0-1 state when all the other angles are 0. And then also fix the omega angle that was previously done to 0. And so gamma would then just be a relative phase between the 2 qubits. And therefore now it's just 2 parameters of beta and gamma that we are sweeping or scanning across. And we actually fix the bond length that we want to investigate. In our case, we thought the minima of, say, 0.7 angstroms made quite some sense. It could be any other bond lengths, of course. We then made a 2D scan across both the beta and gamma parameters to visualize the energy landscape. So what came out was rather interesting, I would say. In a control systems perspective, the exact energy, yeah, that we want is circa around minus 1.1, so around here. However, the energy landscape within, say, the spin 2 device was about minus 0.6 to 0.6. So therefore, we are only seeing a controllability of within this range. So in control systems perspective, this energy is beyond the control parameters for the hardware, and that is the actuator saturation and the given circuit ansatz, of course. So the devices would probably not perform that well either, even if error mitigation was used. And also, of course, the same situation we see over in the STAR-15 device. In contrast, of course, the idealized circuit model ansatz would be controllable for both ideal circuit simulators. And it indicated to us that maybe a different algorithm approach should be thought of for these devices, maybe. And in doing the sweeps, we get a sample of 625 data points, so 25 each. Now we can actually do some timings profile. Each cell corresponds to the time taken to sample a data point from either the hardware or simulator backends. We see that, of course, due to the cloud API, we get latencies and delays in acquiring the results. And you can actually take this with a grain of salt, but I think I've seen experiments with more complex schedules that are completed within, at most, in the order of 1 to 2 minutes. That said, they're all directly controlled by a control computer located just next to the QPU. So network latencies were definitely not a problem there. So in contrast, we're seeing the mean time taken for both the spin 2 and the Starmon 5 to be about 100 to 400 seconds thereabouts. And what we actually do notice are some of these points that are quite outliers within the spin 2 system. We couldn't, we were wondering what could it be. Does anyone want to hazard a guess? I mean, I'm opening up to the floor right now if it's okay to Shuba.
Hey, Kelvin, this is Richard.
Hey.
Speaking. Yeah, it's a wild guess, but I don't know which numbers you took for determining the time. But apart from network latency and all these things, the queuing time within the system, or when the system is calibrating, that also is of influence of the results that you're seeing. So when you send in a job to Quantum Inspire, it will be put in a queue. If you have too many jobs in the queue, as you may know, you have to wait a while before you can put in another job, because you have a maximum of 3 jobs that you can have in the queue as an individual user. But if there are other users before you that are in the queue, you'll have to wait for your answer to return before the queue is at your space. And when the system is calibrating, it just starts calibrating when it's needed to calibrate, and then your job also remains in the queue. So this can add up to let's say half an hour of waiting time for your result to come back.
Actually, yeah, it is exactly that. The outliers are actually due to calibrating times procedures, which are automated. If I think so. So it would be actually nice if I knew beforehand that the system would be doing that before I queued the entire variational job, let's say.
Yeah.
But these are just one of the experiences that we get. And even though in this heat map that we see Starmon 5, also there's not much outliers. There are quite a lot of times that during the weekends that when we ran the study, it can be offline, and we did not really get much feedback from the SDK about that. I think that was during the end April and early May runs. But this is luckily we actually managed to get at least 1 or 2 runs that are good for stuff.
Yeah.
Pretty cool. So these are some of the issues only that we have encountered when we ran the experiments. They are mostly over either controllability over the lower level APIs. So maybe we can do some better scheduling, or even maybe manually add some calibration points when we do the readouts, I think. The controllability is there when you want to run algorithm. It's still kind of stuck to the, let's say, rigid circuit-based models from quantum information processing. And also in terms of the timings for network delays, And also we had that kind of a lack of indication of the backend status through the Quantum Inspire SDK. These issues are not insurmountable, and they are issues which we can actually engineer ourselves away. So after those messages, I mean, what do we actually need for the, just thinking out loud, the next improved Quantum Inspire for it to be useful in variational algorithms? And I would think that we could address the controllability and the software stack first. We've actually seen that the controllability was an issue for the API, since in an actual device, all those gate operations are actually translated to pulses that are being sent to the QPU. Thought would be, what if we expose such control pulse level tools to the algorithm level, so that more advanced users can fully take advantage of the hardware? And I would think it's more of a truly hybrid algorithm, mixing both quantum information processing concepts and also the experimental physics to eke out the best performance from a particular hardware. And for example, is let's say we have a VQE ansatz that is fixed from quantum information processing. Maybe we can mix it up with adding some of these pulses from or experiences from the experimental physics domain in getting better readouts, for example, or better measurements. And based on that, we would say that, yeah, Quantify scheduler and allows such mix of these paradigms. Since we take care of the hard work of translating these pulses to the actual hardware, we can see that the trick is to actually know that they are the same operation, but just different representations of it. So gates and pulses, yeah, they are quite similar. For example, an X90 gate is probably just a Gaussian light pulse with some particular amplitude and width, which are being sent to a port for a particular device. And with that, we can actually work on exposing this abstract pulse level controls over to the algorithm user. Yeah, in order to fully, let's put it this way, to better control the hardware. And after the algorithms improvements, we can also we need to think also how to tackle the network latencies. I would say that having a HPC-like queuing system would make perfect sense. And we can actually send a variational job over to the queuing node, and the node should know that it's supposed to run until success. Something like a Slurm ++ would be beneficial. So for example, is if I'm an end user here, I would send the variational job and also maybe the optimizer object, the method itself, over to the HPC, say a node 0, which is directly connected to the control PC. And then we can actually have feedback over to the dilution fridges and the QPU itself. And this will be the classical state with node 1 N. And this represents the classical HPC that will run the optimizer, and then you can actually have a run till success. And then once it's done, you can actually send back the results of the optimizations. Yeah, study.
Actually, we're looking into these kind of solutions for the future. This, however, is one that's a little bit later on the roadmap, because this requires really a tight integration between your HPC system and your QPU, and also requires authentication through the HPC center, and HPC being, let's say, more the master and QPU being the slave. One intermediate step that we are currently working on is, for instance, being able to send in multiple jobs at the same time, which are then processed as let's say one job. So you don't have one job and then you get your next job in the queue. But for instance, you could do all of the different bond lengths in one go, then do an optimization for each of those bond lengths, and then send in another job that does all the 20 bond lengths or whatever you want to do. Also in one go. That would also speed up the whole system quite a lot already as a first step. So you can send in bundles of jobs.
Yeah, indeed. I would say, as long as we got a solution that, let's say, reduces the latencies and the queues, that will be really good already.
Yeah,
something very beneficial. Yeah, but ideally, of course, you would have the power of the HPC for the classical optimization step, and then on-site inside this HPC, we got a full QPU for it to control. And of course, I think that's the I would say ideal, but yeah, a really nice system to have.
Yeah.
But it's not easy. I definitely understand that. Yeah. So actually, without further ado, I think we could just go on with the demonstration section. And during the demo, just feel free to, again, be interactive and ask any questions about the presentation that we had just now, or in the demo itself, especially when we're waiting for the results. All right. Now, I think the only thing is, how do I? Ah, okay, I can see my preview of the screen. Very good. Stop lab. Yeah, probably. Okay. So we start first with the, let's say, the simulator and the full VQE run in a noiseless simulator, of course. And in our case, we are using the Quest simulator as a show. Since surprisingly, well, the Quest simulator is at least 10 times faster than CIRQ. Yeah. So we load in all the relevant modules, and we set the saving of the data set in the test directory. She automatically does that. We're turning off live plotting for now because we are optimizing over 4 parameters, and yeah, it's quite difficult to visualize a 4 or multi-dimensional optimization stuff. Let's see. And we're just creating a local backend for the CIRQ Quest interface and simulator. And now we're creating the relevant measurement control objects, one which is nested within the other. The reason being that if we're doing a full VQE, the inner or the nested measurement control would be handling the adaptive and the variational algorithm itself. And then the outer measurement control would be doing the sweep across the different bond lengths. And we use, of course, OpenFermion to load the molecular data. And this is hydrogen, just a reminder. And then within CIRQ, we create the circuit ansatz, and you can see, yeah, it's exactly the same, alpha, beta, and gamma, omega. We also, if we want, we can also start the CIRQ backend. And we use QCode's instrument parameter as some sort of a holder to make our data collection a lot easier. And then we also define the relevant gettables and settables. In this case, we are setting this alpha, beta, gamma, and omega parameters. And then we're getting the cost function with either using the local backend, which is the Quest simulator, or the CIRQ backend. And then we also define a stopwatch gettable. In this case, it handles the timings and the profiling. And then we feed in a sci-fi minimize object, and that would be our adaptive function using Kobila, some of the options there. And we're using the Quest gettable. And then this is meant for the bond length sweep. And then we finally run with the initial angles being set at zeros. And so it can take about 2 minutes. So if you all got more questions, just feel free to talk. So what's happening at the moment now is it's finished the first bond length, the adaptive run, and now it's trying to optimize for the second bond length, and then so on and so forth. And we always get the results saved and stored for free via the framework. We can always revisit them later on. This gettable, of course, saves the II, ZI, IZ, and all of the parameters per bond length. And these will be the optimized alpha, beta, gamma, omega angles.
So on the classical side of this, what kind of like what is running the actual optimization routine? Is it something in SciPy, or did you write your own?
Yes, SciPy optimize.
Oh, yeah, okay. So this is just like the bog standard thing that is provided with SciPy. And do you like, is it possible to make other choices, or is this?
Yep, as long as your interface is exactly the same as the minimize function, so which I will be showing later. The fake VQE part, you can see how we actually mock the interfaces of SciPy optimize, and then it would just function the same way. Yeah. So we're almost done. And so I think the CMA-ES would be a really nice optimizer to use and study. But we didn't do that. It's time limitations.
Yeah, because how much does like the quality of this depend on just having a good classical optimizer? Is that? I mean,
I think
probably doesn't matter, but for these sort of finite instances, are there any differences?
I think in terms of at least this study, I don't think the quality of the solution would depend on the optimizer. I mean, it's relatively simple. It's just four parameters that we're optimizing for, and in actuality only one. But yeah, maybe in the future, if we have many more classical knobs to optimize for, then yeah. Or I can imagine that if you go for a very, let's say, hybrid algorithm approach, hybrid in the sense that you want to do some pulse shape optimization as well, then I can imagine then you would need a very nice, elegant optimizer. Yeah, so it's done, and then we can actually explore the data set that we got. We get this timings profile per bond length that we get for free also. And these are the optimized parameters that we can actually put in to the next, the hardware. And we see that, of course, the alpha parameter is always at 5. Yeah, and then we can actually plot this. Nothing really surprising. It's an ideal simulator, so it should be really good in terms of the profile qualitatively. So let's also just out of curiosity, we want to see if we want to see or investigate a single bond length, what the optimization procedure is like. We can load the data set also and say 0, 1, 2, 3, 4. Let's say the fourth one, which is a bond length at 0.7. See that, okay, it took about 328 iterations of function evaluations to get to the optimal value, and then we also see the convergence plots, and we can do that, relatively easily. Yeah, that is this, say, noiseless full VQE run, and those angles that we got, we actually sent it over to the hardware. And in this case, I can actually show how you would mock this optimization function if you got a custom one. So let's load it up. And just for, avoiding any potential conflicts, we say that we're going to do it in the hardware. We also turn off live plotting. This is exactly the same copy, only with some tweaks. Okay. And then just to assure that we're using the same circuit and also the same parameters. And the only difference is now, of course, we get the spin backend involved. And this is what your question, I think, Jonas, was. So we have a mock optimizer function. You give it the same interface as the SciPy minimize or optimizer function. Yeah, you're good to go. And then since we're sending it over to the hardware, I want to have a debug there just to ensure that we get, to know everything that we're sending it over. Stop gettable, settables. And over here, this is where, your adaptive function, you would actually just put in the object itself. The mock optimizer, that is. And then we say that, okay, we are using the spin to gettable. The rest is exactly the same. And once I turn on here, we're actually sending this over to the hardware, and hopefully I can show you it's all working. So it's executing. So we can actually wait a bit. So this will take, I think I'll of course, this is just showing it. So maybe 1 or 2 points, and then I'll move on. So within each bond length, we actually need to evaluate 3 circuits, right? So the ZZ, the XX, and the YY. And that could potentially be saved into one, actually, if you just send the exact same schedule and then know that it's supposed to measure the XX and the YYs, then it could be subschedules, that concept where, we don't need to send in 3 extra steps. So let's, so once we get some results, we will get the JSON files.
So I'm actually not entirely sure how this works, but if you're just sending like a QASM file to the quantum computer, and then it runs it and it sends some results back. And is that like is that like the sum total of possible interactions, or is it also possible to sort of have your classical computer communicate like dynamically with the quantum computer? Because if you want to do more than one iteration, you want to keep doing this, right?
Correct. So that's what I meant by the current limitations of cloud-based APIs, right? So we can have a classical optimizer running within our own system, but then you still need to send one by one these circuit evaluations over to the cloud. Hopefully it finishes fast, and then it returns back the result for one iteration. And that's also the reason why we did this fake VQE, because we just cannot afford to have thousands of these evaluations. Otherwise, it'll just take too long. So we already have one result, and you can actually see what has been sent for the first bond length. And if we have the debug mode on, we actually can figure out what the XXYYZ circuits were being sent to Quantum Inspire, and also their relevant probabilities. This would be if we turned on the debug mode. So I think I will terminate this, and it took about 105 seconds to get the evaluation done. That means we also need second one. So good. I will terminate it now.
So how much of these 105 seconds are just the computer communicating back and forth, and how much of this is actually the quantum computer running?
Yeah, so if you notice, so if it was local, I would think, it would be around 2-3 seconds at most.
Oh, okay, yeah, it's a big difference.
You can go to the results in Quantum Inspire and look at the actual execution time, the QPU time that was needed.
But I don't think I can see that now, can I? Because
if you go to your results file, click on the results object. Oh, this one is running.
It's still pending.
Yeah, it's still running.
Yeah, but then but then the moment that it is finished sending to the SDK, then this project gets deleted.
Okay, yeah, that's something that you can have as a setting. But if you normally you could try it out yourself. If you send an algorithm to Quantum Inspire, for instance, not through the SDK but through the web frontend, and you go to the results file, you'll see that it has a property attached to it, which was the execution time, and this was the actual execution time on the QPU. So this is without the latency and all that stuff. It does include time to upload the circuit to the control electronics, etc. So there's some other latency included as well. But this is more realistic than, let's say, the actual return time for the job result.
Yeah. So I would imagine then at most it will be about a second or two then. If it was directly
it depends on the number of shots.
Yeah, of course. Yeah. So just to show that we've interrupted, and say the framework is safe in terms of such interruptions. We can also inspect the data set. Of course, the bond lengths that were not done, it will have nuns, but it doesn't deter the plotting of such a thing. And of course, we get from the spin2 backend. So we have also already seen the full, let's say, version, there's a full VQE as well as running in the hardware. We needed to do this 2D scan of having two parameters, and still the same. And this time we can actually do live plotting because it's just two parameters. Sorry. So we will still carry on using, let's say, the fake, or rather, the simulator to sweep, since it wouldn't be too tangible to have 625 evaluations of over in Quantum Inspire. But it's the exact same circuit with pi fixed and 0 for omega. We use, of course, the 0.7 bond length index, CIRQ, and again using the mock optimizer, which actually just does nothing but return the cost function evaluation at the angle that was input. And we are only varying the beta and gamma. And in this case, we only needed one measurement control. So it runs, see the live plotting goes there, and it's doing the sweep. And this is the energy landscape when we vary beta and gamma. And these are the cross sections of it. And we can actually have a look also. Since it was in debug mode, we can actually have a look at see what the individual results for the simulator. And yeah, this is guaranteed to be compatible with the Quantum Inspire CIRQ. Yep. The file. We have the timings and the energy landscape. And of course, we already saw in the presentation that, yeah, this is the ideal energy landscape. And these were the times. Yeah. So almost 3 seconds for a single circuit, function evaluation. Yep. So we do have about 10 minutes left. Then I can quickly just show what I meant by using Quantify Scheduler and what I also meant by translating the pulses when you actually run a quantum algorithm and the hardware. All right. This is from the tutorial of the Quantify Scheduler repository. And we have, say, the CZ, the RXY, and the RX90 for the Bell experiment. And in this case, we are sweeping across the theta values for RXY gate. You can also see the schedule. So this looks like a circuit model here now, but once we add in some hardware data and some constraints of the hardware, then we can actually see that within each operations that you send, you're actually sending in a pulse to a particular port in the device. And so this would correspond to the X90 gate, and then this will be the RXY gate. And then we can also see the CZ gate to the different ports. And these are actually being translated. And that's the reason why in the future, maybe a nicer variational algorithm could incorporate this approach, where suppose I start with this, say, VQE ansatz. And we saw that it is it's beyond our control within the hardware. Maybe in between, we could add some kind of more physics-based pulses if we're aware of the hardware limitations, and maybe get better readings from that. Yeah, and this is fully supported by the Quantify Scheduler module. So with that, I think the demo part is also done. Yeah, so I would like to thank, before I leave, I just wanted to give some appreciation and some disclaimers from my side. and the appreciation to the folks who have actually worked tirelessly to produce Quantum Inspire 1.0. And it's all about making a better system, right, for the future. Thanks. Feel free to ask questions now again.